Houston, Tranquility Base here. The Eagle has landed.
We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
ABC News presents Footsteps on the Moon, the flight of Apollo 11.
Good morning, ladies and gentlemen. I'm Frank Reynolds at ABC Space Headquarters in New York. It is July 16th, 1969, and we are all about to witness the fulfillment of that promise that President Kennedy made at Rice University Stadium in Texas on September 12th, 1962. The moon that still has not set in some parts of our world has only a few more days of what you might call untrammeled history. These three men are about to embark on certainly one of history's most glorious adventures. Commander Neil Armstrong, Lunar Module Pilot Buzz Aldrin, and Command Module Pilot Mike Collins. Armstrong and Collins have already entered their command module, and Buzz Aldrin will be entering to join them in a few moments to begin this epic journey, and we shall all see it. ABC Science Editor Jules Bergman is at the Cape. There has been a minor difficulty developed there at the Cape, and let's get a report from Jules now on just what is being done. Good morning, Jules.
Good morning, Frank. We're at T-minus 2 hours and 28 minutes into the scheduled launch of Apollo 11 at 9:32 a.m. Eastern Daylight Time, and the countdown has been going spectacularly until about 10 minutes ago, just before Neil Armstrong, Mike Collins, and Buzz Aldrin started to get into the cabin of Apollo 11. And then a slight leak developed in a valve system that replenishes the liquid hydrogen for the third stage of the Saturn V, the S4B stage. The valve in question is not on the spacecraft itself, but on GSE, or ground support equipment. It's the same valve, the very same valve, by the way, that leaked back on Apollo 10. Everything else here, Frank, is holding up very well. There's a forecast of clouds at 15,000 feet. As we look back to pad 39, right directly behind our ABC News Space Headquarters here at the Cape, you can see the clouds over the ocean. They haven't yet truly developed over the land area, and if it stays this way, everyone in the country and millions of people gathered around Central Florida will get a spectacular eyewitness view of Apollo 11 and the Saturn V lifting off. As it is now, there's a light layer of cirrus clouds at about 15 to 20,000 feet over the Cape. They could cause some interference with visual viewing, but not with the launch itself. The launch limits have gone down really much, if you will, on this fourth launch, we should say, of the Saturn V, fourth manned launch, fifth unmanned. As of now, the weather is good, the countdown going well, except for this liquid hydrogen leak, which has to be fixed, and there's no reason to think we won't lift off at 9:32 a.m. Eastern Daylight Time as scheduled. That's the story, Frank.
The astronauts of Apollo 11 awoke early today and began their ritual-like preparations for this blast-off to the moon. One of their doctors, as I told you earlier, said they appear rested, fit as a fiddle, and ready to go. They actually had about 8 hours of sound sleep, which is probably more than a good many other people who were preparing for this launch today. They had a big breakfast of scrambled eggs, steak, toast, coffee, and orange juice. And for a film report on their final meal on Earth before blasting off, here's Jules Bergman at the Cape.
Crew astronauts Armstrong, Aldrin, and Collins were awakened at 4:15 a.m. this morning, just about 3 hours ago, after having gone to bed about 9:20 last night, and immediately after a quick medical, had the traditional astronauts' breakfast of steak and eggs. There's Buzz Aldrin, the lunar module pilot. We saw Mike Collins a moment ago. Spacecraft Commander Neil Armstrong, who'll be 39 on August 5th, just a few days from now, led by security guards, greeting a farewell as they get into the transfer van for the 3.5-mile ride to pad 39A. Neil Armstrong leading the way, then Mike Collins, and finally Buzz Aldrin.
We're back at ABC Space Headquarters in New York, awaiting the still scheduled launch at 9:32 Eastern Daylight Time this morning of Apollo 11. The commander of the mission is 38-year-old Neil Armstrong, the only civilian among the three-man crew, and of course the man scheduled to take the first actual step on the moon. The pilot of the lunar landing module is Edwin Aldrin Jr., 39 years old, and an Air Force colonel. 38-year-old Michael Collins, a lieutenant colonel in the Air Force, is the pilot of the command module. It will be his job to circle the moon while Armstrong and Aldrin are down on its surface. Jules, did you have any difficulty getting out to the Cape this morning?
Frank, we had no difficulty, but we practically didn't get to sleep at all last night just to be sure we wouldn't have any difficulty. The shot we're looking at from the helicopter now is over Highway A1A, the main north-south road along the Atlantic, and we're looking at the beach just below the South Gate, the old Gate 1 of the Cape where we came in this morning. You know, the drama may be here at Pad 39 and on the moon this Sunday, that unforgettable drama, but it's somehow, for me, also on the roads around this spit of land which Spanish explorers 352 years ago landed on and called Canaveral, for the fields of sugar cane. That's what Canaveral means in Spanish, cane fields. The fields of sugar cane they found growing here. We passed 10,000 odd cars, what we guesstimated, parked around the Gate 1 area at 4 a.m. when we got here, cars from every state, with little kids staring wide-eyed at the Saturn V glowing in the huge xenon spotlights 15 miles away. And we saw teenagers with telescopes. It was the very same road we came over 8 long years ago, 21 manned space flights ago, when we came out at just about the same hour to cover Alan Shepard's 15-minute suborbital hop, America's first manned space flight. Americans cared then, I think, and they care now. And it was a very moving scene for me because, well, we were tired. They were tired. They'd been up all night. All those thousands of people who we see now in daylight in those cars parked along the road that our live helicopter is showing us. Indeed, the helicopter pilot this morning, Bob Lockrow is his name, was the same man who used to fly us here with the very first film switches we did on flights and the very first live things. There's good luck Apollo 11 engraved in the sand. All going very smoothly here with the count. Among the distinguished visitors here this morning, along with Vice President Spiro Agnew, is the former President Lyndon Johnson. There's our live picture from the VIP stands on the other side of the VAB and Launch Control Center. Behind the former president is former NASA Administrator James Webb, sitting in the picture, and many other dignitaries gathered there. Some 8,000 dignitaries in all invited by the space agency as guests to be at this launch. And there's Mrs. Johnson being greeted with the former president.
42 minutes and 44 seconds away from liftoff now of Apollo 11, which is about the size of a United States Navy destroyer, as we pointed out to you a bit earlier. It stands higher than the Statue of Liberty, and it is the most sophisticated space vehicle in the world today. It is made up of 5 separate parts. Jules Bergman has the story on it.
Apollo 11 contains the lunar module, or LEM, which will weigh more than 32,000 pounds at launch time. The command module serves as a flight operations center and living quarters for the astronauts. After the third stage rocket sends Apollo 11 toward the moon, the onboard service module engine will be used to put the astronauts into lunar orbit and later to return them home to Earth. The total payload, nearly 100,000 pounds, rests on a Saturn V rocket. The first stage generates 7.5 million pounds of thrust at liftoff. The second stage will carry the Apollo spacecraft and astronauts to an altitude of 100 miles. And then the third stage breaks Apollo 11 out of Earth orbit and propels the astronauts toward the moon. And this is what Eagle, the lunar module on Apollo 11, will look like after its legs are, its gear is put down after translunar flight has begun and as it heads toward the moon. In addition to this black and white covering, of course, it's covered by gold and black thermal foil, if you will, mylar foil, and black foil to protect it from heating as it heads around into lunar orbit and then down toward its descent on the moon. But essentially, that's what the vehicle looks like, a very ungainly machine. The astronauts still call it a thin, light-walled flying machine, a thin, light-walled structure, but it has proven to be one heck of a good flying machine on 2 flights now, Apollo 9 and Apollo 10. Launch control is telling us now that things are proceeding very smoothly with the fueling and with topping off the liquid oxygen in the S1C, the Saturn main stage, all going very smoothly at T-minus 40 minutes, and we're lifting off at 9:32 a.m. Eastern Daylight Time as of now, everything proceeding very smoothly toward that pre-calculated liftoff time.
2 minutes, 10 seconds, and counting. The target for the Apollo 11 astronauts, the moon at liftoff, will be at a distance of 218,096 miles away. We've just passed the 2-minute mark in the countdown. T-minus 1 minute, 54 seconds, and counting. Our status board indicates that the oxidizer tanks in the second and third stages now have pressurized. We continue to build up pressure in all 3 stages here at the last minute to prepare it for liftoff. T-minus 1 minute, 35 seconds on the Apollo mission, the flight to land of the first men on the moon. All indications coming in to the control center at this time indicate we are go. 1 minute, 25 seconds and counting. Our status board indicates the third stage completely pressurized. 80-second mark has now been passed. We'll go on full internal power at the 50-second mark in the countdown. Guidance system goes on internal at 17 seconds, leading up to the ignition sequence at 8.9 seconds. We're approaching the 60-second mark on the Apollo 11 mission. T-minus 60 seconds and counting. We passed T-minus 60. 55 seconds and counting. Neil Armstrong just reported back it's been a real smooth countdown. We passed the 50-second mark. Power transfer is complete. We're on internal power with the launch vehicle at this time. 40 seconds away from the Apollo 11 liftoff. All the second stage tanks now pressurized. 35 seconds and counting. We are still go with Apollo 11. 30 seconds and counting. Astronauts report it feels good. T-minus 25 seconds. 20 seconds and counting. T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
We got a roll program.
Neil Armstrong reporting the roll and pitch program, which puts Apollo 11 on a proper heading.
Slowly, but gathering speed. Going beautifully, burning hot.
Plus 30 seconds.
Roll complete and pitch is programmed.
One Bravo is a abort control mode. Altitude's 2 miles.
All 11 Houston, you're good at 1 minute.
Downrange 1 mile, altitude 4 miles now. Velocity 2,195 feet per second.
She's going beautifully.
We're through the region of maximum dynamic pressure now.
Apollo 11, 42,000 feet.
17 miles an hour, pitch range 12 miles high, velocity 4,000%.
Stand by on mode 1 Charlie. Mark, mode 1 Charlie. 1 Charlie.
Cliff Charlesworth taking a staging status.
This is Houston, you are go for staging. Inboard cutoff.
Inboard engines out.
I'm inboard cutoff.
inboard cutoff exactly on schedule. Apollo 11 now 3,000 miles, now doing 3,650 miles an hour.
Downrange 35 miles, 30 miles high. Standing by for the outboard engine cut down now.
Staging. And ignition.
Armstrong reporting staging and ignition. The first stage engines have burned out exactly on schedule. The second stage engines have lit off.
Houston, thrust is go. All engines, you're looking good. All right, Roger, you're loud and clear, Houston.
41
At 3
miles.
minutes, downrange 70 miles, 43 miles high, velocity 9,300 feet per second.
We got skirt step. Roger, we confirm skirt step.
Apollo 11 going a little faster than expected, but perfectly within
Neil
limits.
Armstrong confirming both the engine skirt separation and the launch escape tower separation.
Houston, be advised the visual is go today. This is Houston, Roger out. Yeah, they finally gave me a window to look out. Houston, your guidance is converged. You're looking good.
Downrange 140 miles, altitude 62 miles, velocity 10,300 feet per second.
11 Houston, you are go at 4 minutes. Roger.
Still in sight from our long-range cameras,
Ground track.
burning hot, straight and true all the way toward a moon 218,000 miles distant. A moment many Americans, many people never believed could happen or would happen.
190 miles downrange now, 72 miles high, velocity 11,000 feet per second.
And the first major hurdles have been passed for Apollo 11. All going very, very well. The first minutes of a 195-hour-long flight ticking off almost without tension, almost like a regular airliner takeoff, but for the thunderous roar of the flame of the Saturn
Booster
V.
says it's looking good at 5 minutes.
11 Houston, you are go at 5 minutes. Roger, you're Apollo 11, go.
We're hearing Neil Armstrong live, reporting back to booster control, Capcom in mission
Downrange
control.
270 miles, altitude 82 miles, velocity 12,472 feet per second.
Slide S4B to COI capability. Okay.
That's 9,000 miles an hour.
S4B to COI capability.
That's 9,000 miles an hour. Confirmation that the
Apollo 11 could now get into orbit using the S4B if necessary.
In your living room. Oh, thank you. You all are coming through beautifully, too.
very clear communications this morning, very clear air-to-ground from Apollo 11. That's Capcom Bruce McCandless, you hear talking from Houston Mission Control. And occasionally Flight Director Cliff Charlesworth in the background. And down...
Everyone's reporting go here in the control center.
So it's 6 minutes, starting to get motors.
And our long-range...
Roger 11, your go from the ground at 6 minutes.
Our long-range cameras have lost the picture finally. Our cameras are now at pad 39, viewing that water deluge or dowsing system we told you about. Hundreds of thousands of gallons of water, saving the pad from being all but wiped out by the heat and the flame. The water is still going, still keeping cool. Our animated view now showing us what's happening up there at 6 minutes and 35 seconds into the flight of Apollo 11.
Between the second stage and the third stage, the fuel uncovers a sensor starting that sequence.
We're coming up almost to the point where the second stage S2 rockets will burn out.
Uncovered at 8 minutes 17 seconds with outboard engine cut off, 9 minutes 11 seconds on the second stage.
Apollo 11's go at 7 minutes. 11, this is Houston. Roger, your go from the ground at 7 minutes. Level sense arm at 8+17. Outboard cut off at 9+11. Roger.
Very close to nominal
Downrange
figures.
530 miles, altitude 95 miles, velocity 17,358 feet per second.
Apollo 11 has almost reached orbital velocity now. It'll require another minute of burn of the S2 second stage. President Johnson in the VIP stands with Lady Bird Johnson, obviously relaxed, happy at the way the launch went, and Vice President Agnew next to the President.
7 minutes, 41 seconds.
Roger, we confirm.
Inboard engines are out on the second stage as planned.
Inboard engine burnout exactly on schedule at 7 minutes 40 seconds. Apollo 11 now about 3 minutes away from going into Earth's orbit over mid-Atlantic.
Apollo 11, go on all sources.
Your go at 8 minutes.
I've just built the mixture ratio shift.
And galloping
We got
along.
PU shift down here too.
Apollo 11 galloping along now at more than 12,500 miles an hour.
United States Board, these thunderstorms downrange is about all.
That was Neil Armstrong. We couldn't make out what he said.
11, this is Houston. You are go for staging. Over.
Understand, go for staging.
Stand by for mode 4 capability.
Mode 4.
Mark, mode 4 capability.
Mode 4 and Apollo 11 could get into orbit using the service propulsion system now. Altitude is 100 miles, downrange 883 miles. Outboard engine cutoff. And ignition.
Ignition confirmed. Thrusters go, 11.
And we have a good third stage now.
Third stage ignition on schedule, speed building up just the way it should. Looking very, very good.
Velocity 23,128 feet per second. Downrange 1,000 miles, altitude 101 miles.
Apollo 11, this is Houston. At 10 minutes, you are go.
Roger, 11, go. Capcom Bruce McCandless giving the reports here from the control center.
A relaxed Neil Armstrong saying, "Ah, Roger, we're go."
Apollo 11, this is Houston. Predicted cutoff at 11 plus 42. Over.
1142, Roger. Downrange 1,175 miles. Velocity 24,190 feet per second. Altitude 102 nautical miles. Apollo 11 still go on all sources.
Apollo 11, this is Houston. You are go at 11.
And ticking away the last 3 seconds.
We're predicting third stage shutdown at 11 minutes 42 seconds.
And Apollo 11 is just about ready to go into orbit in a few seconds from now.
Velocity 25,254 feet per second. Downrange 1,400 miles now. Altitude 102.8 nautical miles. Shutdown. Shutdown right on time. 1.4 by 103.6.
Roger, shut down, and we copy 101.4 by 103.6.
And Apollo 11 is in orbit. Scratchy.
Apollo 11, this is Houston. You are confirmed to go for orbit.
When the third stage is fired, the astronauts will then be inserted into an Earth parking orbit.
the guidance system has already computed the trajectory needed to intercept the moon. The confirmation of that trajectory or course will be relayed by Houston to the astronauts. 2 hours and 40 minutes after launch over the Pacific, the third stage engine will be restarted, and when an escape velocity of nearly 25,000 miles per hour is reached, Apollo 11 will be injected into a translunar trajectory. Soon after, the panels of the spacecraft's lunar module adapter are jettisoned. The Apollo Command and Service Module then separates from the booster. The astronauts start the docking maneuver, rotating Apollo 180 degrees, and then, using their small thruster rockets, dock with the LEM. The third stage will be jettisoned when the docking maneuver is completed about 2 hours after translunar injection. The astronauts, using star sightings backed up by mission control, guidance radar, and computers, then work up the data to make mid-course corrections and set their course to intercept the moon 3 days later. Depending on how accurate the rocket engine burns to get away from Earth, none or as many as 3 mid-course corrections may be needed. Apollo's speed decreases from 25,000 to less than 4,000 miles per hour en route. Then, near the moon, as lunar gravity begins to exert its influence, the speed of the spacecraft increases up to 6,000 miles per hour. Apollo 11 is in a free return trajectory, which will carry it around the moon and back to Earth for recovery if problems have developed. But if all has gone well, Apollo 11's onboard service module engine will be fired and the spacecraft will be placed into lunar orbit. Because of the danger of mechanical failure, all of the systems can be overridden by the astronauts if the automatic systems aren't working perfectly. 81 hours into the flight, Armstrong and Aldrin transfer into the lunar module for the second time, completing their checkout of the lunar landing spacecraft. They remove the docking probe and drogue from the tunnel connecting the command and lunar modules and equalize the pressure in both vehicles. The lunar module pilot then floats through the docking tunnel overhead and into the LEM. One of the first tasks for the lunar module pilot is to activate the LEM's environmental control system and to change his suit connections to the LEM's umbilicals. Now, today the moon is the target, and we're going to get the word on that TLI burn coming up in just a moment now from Mission Control. And we're now 14 seconds away from TLI burn. Mission Control is counting down. There's ignition. There's the word from Mission Control. Ignition over the South Pacific for the translunar insertion burn.
We confirm ignition, and the thrust is go.
Thrust is built up to get them headed up to escape velocity speed of 25,000 miles an hour. The burn took place over the southwestern Pacific 2 hours and 24 minutes into the flight of Apollo 11.
Guidance looking good.
Let's go to Mission Control now for the talk down to the separation maneuver.
This is Houston, we copy.
Capcom McCandless saying he copied, but we very faint transmission. Let's see if we can pick it up now.
We confirm the separation here on the ground.
Separation confirmed. The third major hurdle of the flight accomplished. Next, that docking and extraction of the LEM.
All right, we now have a picture from Apollo 11, so let's go to Houston for the conversation between the spacecraft and Houston, and we'll see these pictures. There's the Earth.
The Earth from 130,000 nautical, or about 149,000 statute miles.
Roger, you're seeing Earth as we see it at our left-hand window, just a little more than a half Earth. We're looking at the eastern Pacific Ocean, and the north half of the top half of the screen, we can see North America, Alaska, United States, Canada, Mexico, and Central America. South America becomes invisible just off beyond the terminator or inside the shadow. We can see the oceans with a definite blue cast, see white bands of major cloud formations across the Earth, and can see the Sierra Mountain Range, the peninsula of Baja California, and can see some cloud formations over southeastern U.S. There's one definite mild storm southwest of Alaska, looks like about 500 to 1,000 miles, and another very minor storm showing the south end of the screen near the, a long way south of the equator, probably 45 degrees or more south latitude.
We were saying, Cliff Charlesworth, that
we can still see the Earth through the left window, and it appears that we can see a floodlight off to the left, either that or some sun shafting through the hatch window.
Almost looks like two Earths.
It's floodlight. Now we're coming in. Can't quite make out who that had. It's Big Mike Collins there. Well, you got a little bit of... Yeah, hello there, Split fans. You got a little bit of me, plus Neil's in the center couch, and Buzz is doing the camera work this time. Roger, it's a little dark now, 11. Maybe a bigger f-stop might help. Yeah, that didn't work. It's getting a lot better now, 11. Mike, you coming in 5 by. Got a good... Well, I put on a coat and tie if I'd known about this ahead of time. Is Buzz holding your cue cards for you over? Cue cards have a no. We have... We are very comfortable up here, though. We do have a happy home. There's plenty of room for the three of us, and I think we're all learning to find our favorite little corner to sit in. The zero-G is very comfortable, but after a while you get to the point where you sort of get tired of rattling around and banging off the ceiling and the floor and the side, so you tend to find a little corner somewhere and put your knees up or something like that to wedge yourself in, and that seems more at home. Roger, looks like Neil is coming in 5 by there, 11. Mike, see you in the background. The definition is really outstanding. The colors are good. It's a real good picture we're getting here of the Commander Armstrong. Yeah, Neil's standing on his head again. He's trying to make me nervous. Roger. He's disappearing up into the tunnel, of course, as he would going into the lunar module, only backwards. Roger, we can see portions of the LAP now, the systems test meter panel in the lower part of the picture, or we did have it anyway. Okay, and then directly behind his head are our optical instruments, the sextant and the telescope that we use to take sightings with. Roger, copy, and we see the disky flashing with a 651. In fact, we can read registers 1 and 2 quite clearly.
That's the computer.
Yeah, the old high gain angles telling us which way the Earth is.
Right. Read the numbers.
Copy. That's a beautiful picture. Clarity is outstanding. We can also give you the time of day in our system of mission elapsed time, 34 hours, 16 minutes, and 15 seconds. Roger, you see that clearly enough, Charlie? Roger, Apollo 11. We can see it counting up every second. We got 34:17:02 now.
Okay, back to the high gain angles. Roger. Swing amp. Now we've amputated those.
Best quality picture we've ever seen from the inside of a spacecraft.
It has to be able to read those numbers like that. It's like a tote board of the racetrack.
Even if it is their computer display keyboard or disk key readout.
11, Houston, we have a beautiful rainbow there, and as you move the camera around, that looks like the star chart coming into view now, over. Yeah, those are Buzz's two star charts that he is using right now as sunshades over the right-hand window, window number 5. Roger, we see the sun shining in through it behind him and plotting out the correction, the ecliptic plane and the stars that you're using for the navigation. You're right. He doesn't really need the charts, he's got them memorized, they're just for show. We copy. Well, we're pointing up in this direction. We see out our side windows the sun going by, and of course out one of our windows right now we've got the Earth. Now right behind my window, of course we have the sun, because the sun is illuminating the star chart that we see. This line represents the ecliptic plane, and these lines, vertical lines, represent our reference system that the spacecraft is using at this time. As we approach the moon will gradually grow larger and larger in size, and eventually it will be in eclipse. It will be eclipsing the sun as we go behind it, as we approach the lunar orbit insertion maneuver. Roger, 11. Could you attempt a little bit better focus there, 11, over?
Looks like Mike Collins is moving the camera around the inside of the spacecraft again, back to Buzz Aldrin's star charts.
And now Aldrin's the only one we haven't seen. He was talking just a moment ago, but we haven't seen him yet.
So part of the smooth pate of his semi-bald head.
11, Houston, that's a lot better on the star chart now. We can make out the ecliptic plane and the planets and the sun and the moon as they're drawn at various places throughout the ecliptic plane, over. Okay, Charlie.
There's Aldrin.
Slightly out of focus shot and a little audio breakup beginning.
If we can get some of the wires untangled here, we'll give you a demonstration of how easy push-ups are up here. 11, Roger. Good view of Buzz there.
One of the reasons these pictures are such good quality is they're using a small floodlight inside the cabin to help illuminate their faces and the instruments.
When it gets pretty hard doing it that way, we just roll over and do it the other way. Roger, we copy. Couldn't figure out whether that was a chin-up or a push-up. Just take your choice, I guess.
Buzz Aldrin going through a complete roll now in weightlessness. And floating his way forward in the cabin from the lower equipment bay.
Here's the champion pole vaulter.
It's probably almost your dinner time down there, Earth. We'll show you our food cabinet here in a second. 11, roger.
You know, Frank, in weightlessness, even I could be a champion acrobat. It doesn't take a Buzz Aldrin. And now we're looking in the left-hand lower equipment bay where the food is stored and prepared. That's probably Mike Collins.
Houston, we see a box full of goodies there, over.
They've
No,
got
we really have them, Charlie. We got all kinds of good stuff. We've got coffee up here in the upper left and various breakfast items, bacon in little small bites, and beverages like fruit drink. And over in the center part, we have, all kinds of things. Let me pull one out here and see what it is. Right. Would you believe you're looking at chicken stew here? All you have to do is 3 ounces of hot water for 5 or 10 minutes. Now we get our hot water out of a little spigot up here with a filter on it that filters any gases that may be in the drinking water out. And we just stick the end of this little tube in the end of the spigot and pull the trigger 3 times for 3 ounces of hot water, and then mush it up and slice the end off it. There you go, beautiful chicken stew. Sounds delicious.
And that's their little emergency flashlight.
Yeah, the food so far has been very good. We couldn't be happier with it. Roger. Flashlight a second. The surgeons are saying thank you there for that. And it is sort of down in a dark corner, so we have a flashlight here to help us see things. And if I can let go of it carefully, it'll just hold itself right where it is. Roger. As long as to disturb it will. Apollo 11, Houston, that's a pretty good demonstration. You started off really stable there, Mike. Well, the problem is no matter how carefully you let go, you bump it just a tiny little bit, set it in motion, and once in motion, there she goes. Try that again. It looks fairly stable now with slow rotation.
A little 13-pound portable TV camera shooting these pictures handheld by the astronauts themselves. Now more than 130,000 miles out in space.
I sent their compliments to the chef this afternoon about the salmon salad. The chef made salmon. Fisher was
Well,
very
so much
happy.
to the food department. I'm going to close up the store down here. Roger, we copy. Charlie, we checked out the cable lengths, and we're thinking we might want to see if we can take the TV into the LEM with us tomorrow for part of the time. Over. Roger, good show. We'd like to see it if it'll reach that far. Over. We'll give it a try. Roger.
And we're seeing Mike Collins closing up the food locker. That was Buzz Aldrin we heard, saying they might take the camera up into the lunar module tomorrow at 56 hours into the flight when they check it out for the first time.
Clear definition there of Collins' face.
The camera has been clamped on using some small hand clamps they use for their still picture cameras and motion picture cameras.
Now, where I sleep is down underneath this couch. Houston, Roger.
And Mike Collins is apparently about to show us a demonstration of his sleep station.
Slowly sinking into the sack there. Yeah, it's really comfortable.
Good morning.
Forgot to give Buzzy's flashlight back.
They carry some 7 of those little emergency flashlights, Frank, which are really meant as survival flashlights in case they come down on the water and are stranded at sea at night. But they end up using them for everything.
Well, the one question that is raised most often, over and over again, talk about redundancy, is why go to the moon? Well, for scientists, of course, the answer is obvious. They feel that the unexplored moon, thus far unexplored, will tell us many things about our Earth that we cannot find out by studying the Earth itself. In making it a comfortable place to live here, we have more or less wiped out its early history. One of our guests throughout our Apollo 11 coverage, we've already heard from him today, is Dr. Robert Jastrow, who is director of the Goddard Institute for Space Studies at Columbia University. We put the question to Dr. Goddard, why go to the moon?
The moon is a poor piece of real estate, and probably lifeless. But for precisely that reason, it is scientifically invaluable. We would like to know what conditions were on the Earth in the first billion years of its history, about 3.5 billion years ago, when life appeared on this planet according to the fossil record. We'd like to know how the solar system was formed and how the Earth itself was formed. These are things that we would like to know in order to understand whether we are probably unique in our human experience in this part of the world or this part of the universe, or whether what we are experiencing on our planet has been gone through many times in many places. Now, unfortunately, this early history of the Earth has been wiped out by the very factors on our planet that make it such a comfortable place to live in. We have running water, and we have winds, atmosphere. They erode all of the record of our past. We have mountain building, which creates the beautiful continents, but it also wears out and turns over and churns around the record or the rocks that were laid down here when the Earth was a young planet. The very life that we have has removed the traces of its own origins. On the moon, however, which we think is probably lifeless, there's no atmosphere, there's no running water at the present time, and we think that the record of its past is infinitely better preserved than it is on the Earth. Just looking at a picture of the moon such as this one shows you countless craters, the scars of meteorite impacts that have occurred throughout the moon's history. There are 100,000 of them or so visible in a telescope on the front face of the moon alone. Now, these craters, which were probably formed by meteorite impacts, have also, or must also, have occurred on the Earth. The same bombardment by meteorites must have occurred. There are, however, very few remains of those craters left. One of the few remaining is the Arizona crater, a crater 4,000 feet across that you can see when you fly, let's say, from New York to Los Angeles in a jet. This is one of 20 or so craters that are still visible on the face of the Earth. The other hundreds of thousands of millions have been worn away and turned over and buried. Because of the fact that these craters still remain on the moon but are gone from the Earth, we are pretty confident that the moon's surface goes back farther than the surface of the Earth. Just as a digression, by the way, I'd like to mention that there was a big dispute among scientists until recently over whether the craters on the moon were volcanic or meteorite impact. I think most people believe that while some of these craters are volcanoes, the majority of them are meteorite impacts. And the reason they believe that can be demonstrated in the studio. When a meteorite comes into the surface of the moon, it has so high a speed that its energy per pound is 5 or 10 times that of TNT. It drills a clean hole in the surface of the moon and buries itself underground, driving a plug of moon rock ahead of it at such a great rate that the plug of rock is compressed and heated to a gas, a vaporized rock gas. When the meteorite comes to rest, then this plug of hot gas explodes, ejecting all the material above it and forming a crater, something like a bomb crater. Bomb craters have exactly the same size and shape as most most craters on the moon, and we think, therefore, that moon craters are bomb craters. I can't explode a bomb in the studio, but I have buried a firecracker in a bin of sand to produce a small crater of the kind you can see in surveyor photographs of the moon, and a crater which in minuscule form has the dimensions, the scaling, and the shape of lunar craters and bomb craters on the Earth. That was very satisfactory because It shows not only the characteristic conical shape of many lunar craters, but it even shows the lip that forms around them and the bits of debris, in this case they're chunks of flour, that litter the field, and it shows these rays, these radiating lines of light material by which scientists always are able to recognize freshly formed new craters on the moon. In particular, this little explosion crater looks just like large bomb craters and like most lunar craters. So I think there's no doubt what the origin of lunar craters, of many of them at least, is. That doesn't exclude the fact that some craters are volcanic, but that's another story, that's another matter. Now, there's a very interesting consequence of the fact that many craters on the moon are explosion craters formed by meteorites. I have a picture of a 500-foot crater which happens to be in the Ocean of Storms on the west limb of the moon. It's actually in the mouth of the face of the man in the moon when you look at him in the sky. And you see in this crater a littering of the field, of the ocean surface around it, with chunks of rock, some of them 10, some of them 20, 30 feet in diameter. The significance is that when we land on the moon, in each of our landings, although the exploration or the region explored is quite small, perhaps the size of a garden plot in the first landings, we will probably find on that garden plot an accumulation of debris, as shown in the next photograph, the surveyor photograph, taken of a region on the moon similar to the regions in which the landings are occurring. We will find an accumulation of debris, as you see in this picture of the moon surface, representing rocks hurled out of craters all over the moon, rocks from all ages of the moon's past, all depths, all places. An excellent sample of the whole moon acquired from the exploration of one small territory. At least we will be finding these things, this variety, if we're lucky. What will we do with these samples of rocks when we get them? Well, the key question always, I think, in discussing the scientific interest of the moon is, does any part of its surface go back to the missing billion years of the solar system's history and the time in which life appeared on our own planet, or does it not? How old is the surface of the moon? There's much controversy on that question. Some of us hope or expect that parts of the moon do go back to that first missing billion years. And partly with this motivation, among the experiments performed on the lunar rocks as soon as they are let out of quarantine in Houston, the single largest block, about 30 or 40 experimental groups here and abroad, will be concerned with dating these rocks. They're dated radioactively using the fact that all rocks on the Earth, and we're pretty sure on the moon, contain trace amounts of radioactive substances such as uranium. They're present in very, very minute traces, I think a few parts per million, but nonetheless enough so that the radioactivity can be detected if one has a Geiger counter. I have one here. It's connected to an amplifier and a microphone so that it gives a visible click every time it's triggered by the passage of an energetic particle through it. You can hear it click once in a while as I speak because a cosmic ray has passed through it. I also have a piece of rock which contains not invisible amounts, but in an invisibly small amount, some radioactive uranium. And as I bring this rock up to the Geiger counter, the proof of the existence of that radioactivity in the rock is in the fact that an absolute cascade of counts comes out of the counter, almost drowning my voice. This radioactivity itself is not the main point. It is not the means used to date the rocks directly. That's done in the following way, that whenever a radioactive uranium atom decays, emitting one of the particles that we just heard being audibly detected by the counter, it is transformed into a new nucleus and eventually winds up as lead. If the rock is very old, most of the uranium in it has been converted to lead. And when you measure the ratio of uranium to lead by delicate chemical analyses, you find very little uranium and a lot of lead. If the rock is young, very little of the uranium has been converted, and when you measure this ratio, you find mostly uranium and very little lead. So the ratio of uranium to the lead it produces by decay measures the age of the rock. We hope when we make that measurement, our experimenters, that they will find some samples whose ages turn out to be 3.5 billion years or more, and supply us with information on the missing pages of the Earth's and the Moon's history. And that will be the greatest scientific prize that we can possibly capture from the lunar exploration. So the paradox of the Moon is that precisely because it is a poor piece of real estate and probably lifeless, with little or no water, for that very reason it is likely to have preserved the record of its past better than the Earth. And in those samples we hope or expect that we will find clues to the origin of the Earth, the origin of the solar system, perhaps even the conditions under which life began on the Earth, and organic molecules that give us a hint of the way in which life evolved out of non-living chemicals on this Earth, if that's the way, in fact, in which it happened here. The surface of the Moon can be the Rosetta Stone of the Earth and the solar system and reveal the answer to ancient mysteries.
Now, here in New York is ABC News commentator Frank Reynolds.
And good afternoon from ABC Space Headquarters in New York. With me is our science editor, Jules Bergman, and we are on the air today to bring you a complete report on some very, very important maneuvers to be performed by Apollo 11. Basically, the spacecraft is now about 1,000 miles from the Moon and is about to move into position to begin the process that will eventually lead to the landing on the Moon tomorrow afternoon. In less than 15 minutes or so from now, Apollo 11 moves behind the Moon to the dark side, and we will then lose voice contact with the astronauts. And after about 6 minutes or so, then we will have this first big burn of their main engine aboard the spacecraft that will put them into orbit around the Moon. Jules, this is where it becomes very, very interesting, right?
Right, Frank. About 19 minutes from now, Armstrong, Aldrin, and Collins will fire up their big SPS, or Service Propulsion System engine, a 20,500-pound rocket engine, to slow Apollo 11 so that it's captured by the Moon's gravity. It's a walloping big rocket engine burn, consuming more than 7 tons of fuel and propellant. And it slows the spacecraft, both the CSM and the lunar module are docked together, from their speed at that time of nearly 6,000 miles an hour to 3,700 miles an hour. It's a tricky time. Armstrong, Aldrin, and Collins are on their own. Behind the Moon, we can't hear them. Mission Control can't hear or see them. There's the Moon turning, and Apollo 11 is swinging up like this in its orbit. It's coming up behind the Moon just about at this time. Now, that orbit will carry them about 70 miles behind the Moon if nothing at all is done, if they don't do the lunar orbit burn. If they do it, and they're turned around in a retrograde position for a braking burn, if they do it, they descend closer to the Moon like this and are captured by the Moon's gravity, and then swing around the Moon any number of times like that. In point of fact, 13 times until they get set for the descent maneuvers and the landing tomorrow as they come around the Moon at that time.
Yes, later on this afternoon, then they'll make another
Right.
Another orbit burn, won't they, to come down still lower?
Right. Now let's look at what's going to happen if the LOI burn shouldn't work. They would come up behind the Moon just like this, as they are, a little bit of break up there, and swing back to Earth just like that, and land in about 45 hours from this afternoon. There's no reason to think that's going to happen. We're coming up very close now on the scheduled lunar orbit burn time, and this is the way it would look through our simulation inside the Apollo 11 cockpit at this time. Armstrong, Aldrin, and Collins going through the enabling maneuvers. Here's Apollo control.
49 minutes. Apollo 11 should have started this long burn. Duration 6 minutes 2 seconds. Delta V 2,917 feet per second. Given that burn, we expect an orbit of 61 by 169.2 nautical miles. Madrid, AOS. Madrid, AOS.
That's it. The Madrid tracking station has acquired signal. And we're hearing Armstrong very faintly in the background, too faintly to understand. Capcom McCandless calling Apollo 11, saying, Apollo 11, do you read Houston?
We are reading you weekly. Go ahead, over.
That's Bruce McCandless calling.
Roger, burn status report follows. Film indication 0, burn time 557. Roll on the pad. CGN minus 0.1. TLI minus 0.1. TTC plus 0.1. WBC minus 6.8. Fuel 390. Hot 380. Flat balance 0.2.
That was it. That was Neil Armstrong reading back his remaining fuel and burn times to Houston. Very scratchy radio communication. The antennas still aren't set, but Armstrong and his crew are obviously in good shape. The LOI burn went perfectly.
As we were saying a short while ago, while we were waiting really to acquire the signal from Apollo 11, Russia's Luna 15 has moved into a slightly higher orbit around the moon. They have, of course, promised to notify Frank Borman that Luna 15 would not in any way, well, they promised to notify him in the event of any substantial change in the flight plan of Luna 15. They have still, of course, not volunteered any information about the ultimate mission of Luna 15, and we don't know yet whether they really do plan to go on down and scoop up some moon rocks and get back to Earth with them before the men of Apollo 11 can do the same. But the Russian flight is, of course, unmanned. We might just go back into history here a bit and recall that day of April 12th, 1961, and our reaction to the Soviet triumph of putting the first man in space. We've looked back to that day quite often since then. Our space triumphs have wiped out, I think, any vestige of humiliation the United States might have felt at that time, but not the memory of it. Here is an excerpt from a program that ABC News did at that time in 1961 with a youthful science editor named Jules Bergman. Look for the Russian animation explaining how they planned to get to the moon. It seemed quite practical 8 years ago. And here is how ABC News noted the one-orbit flight of Yuri Gagarin, the first man in space.
Historic day, one of the most unforgettable of our century. The point of departure for man seeking to reach space. And this man, Yuri Gagarin, major in the Soviet Air Force, is the first to cross the frontier into the unknown of space. 27 years old, quasi, handsome, highly trained, married to a medical student, the father of 2 girls. Occupation, cosmonaut, the world's first. He has now traveled faster, higher, and farther than any man in the history of this planet. And no other man can yet claim the same occupation or distinction. Tonight, all Russia has gone wild with joy. Delirious crowds in the streets of Moscow, Leningrad, and other cities, hailing the triumph of Soviet science over the West. Russia calls it an unparalleled victory of man over the forces of nature, an immense achievement of science and technology, and the triumph of the human mind. And it is indeed all these things. Now the world is asking, what next? What will Russia try to conquer next in this new world of space? This is what the Russians have in mind for us, a film preview of the future from Soviet science. We're looking at a portion of an extensive film animation prepared by the Soviets of a projected trip to the moon, one they claim will be a reality in the next 5 to 10 years. At the beginning of such a flight, a spaceship propels a multi-stage rocket. As the speed increases, the rocket breaks away, and then various other stages of the rocket also fall away. After a time, it is traveling by inertia alone with no further energy required. Powerful radar stations keep the rocket within the grasp of its radio signals. And automatically operated instruments on the ground send radio impulses back to the rocket from the Earth. And they're received by ground stations. This station guides the rocket with the help of machines to count the electronic impulses. The rocket races forward along an orbit that has been calculated months in advance. But at a command from the Earth, it can launch into another orbit. When a rocket has traveled beyond the Earth's gravity, it can head toward its goal, the gravitational field of the moon. Now a refueling rocket sets out from the Earth, and now our rocket is headed into the moon. When it reaches the moon, a laboratory and tank beds will launch out to explore the moon. The Soviet scientists who designed this project describe it as fully possible. And it may be the next step for the Russians. And so the pattern of Soviet triumph in space. Where are we ask tonight. Our Project Mercury will get off the ground in its first short manned shot near the end of this month. A short ride, 115 miles to the edge of space. April 28th is the earliest date. As for an orbital flight, like Russia did today, that won't come until near the end of the year, maybe not even until early next year. And how do our Mercury astronauts feel about the Soviet triumph? Disappointed, they all tell us today. Naturally, we wanted to be first. 10 days ago at Mercury headquarters, Langley Field, Virginia, I asked Lieutenant Colonel John Glenn, who may well be our first astronaut into space, how he would feel if the Russians beat us into space.
John, if the Russians get a man up before we do, how would you feel about that?
Well, that's a good question because we've been asked this many times. There's only one answer to that. It doesn't change our program one bit. This is like saying that because Henry Ford started a new car first, no one else should be in the automobile business today. The General Motors should have dropped out before they started. Well, this is ridiculous, of course, and it's probably a ridiculous example, but the fact that the Russians happen to get a shot off or may not get a shot off a little bit before we do doesn't alter the objectives of our program a bit. Our program is not set up just as a race to space. We're well aware of the international implications of this, but this doesn't alter the step-by-step progression that we want our program to go through to see that man safely starts space exploration. We have our goals, I guess they have theirs, and the fact that they do or do not get a shot off ahead of us will not alter the objects of Project Mercury.
We're not going to change our plans.
No.
And good afternoon once again. We are, in fact, about to see more pictures now from of the lunar surface from Apollo 11. With me here in our space headquarters in New York is our science editor, Jules Bergman. Jules, these should be interesting shots.
Frank, Apollo 11 is now on the near side of the moon, coming up on the Sea of Tranquility, the landing area where Armstrong and Aldrin are scheduled to land tomorrow at an altitude of 102 miles, and we're just getting the TV picture. Let's go to it for Apollo control.
Apollo Control, Houston. We acquired TV at 78 hours, 24 minutes, 11 seconds. Currently, our orbital parameters show 104. Altitude, an apoloon of 170.2, a paraloon of 61.3 nautical miles, those are.
Well, this is Houston. Would you care to comment on some of these craters as we go by? Roger, we're approaching the approach path to ignition. This is equivalent to 13 minutes before ignition, and we're at about 80 degrees east, I guess. 83 degrees east. Would that correspond to location you're holding in present time? Roger, we're showing your present position is about 76 degrees east, looking back towards the east. Hey, you should be looking back at my Zeno. Roger.
And the
we've now heard from all three Apollo 11 crew members during this television pass. The individual talking earlier was Neil Armstrong.
Ranger Schubert. And Gilbert U is in the center right now. And this comes up at about a little over 12 minutes before power descent. Instead of looking back at it, we'd be looking straight down at it at that time. Roger.
11 now flying
I'll show you an
backwards.
altitude now of about 110 miles, and of course you'd be considerably lower at the initiation of powered descent.
This is exactly the same territory Eagle, the lunar module, will be flying over tomorrow as it begins its powered descent toward a landing on Lunar Landing Site 2, now about 100 miles to the west of where we are.
Look at register 3 on the Disky theta. Theta is increasing toward my desired of 315, and I'll let the hand controller alone here, and I'll bet you it reverses itself.
They're just now passing out of Smythe Sea, heading along the lunar equator toward the Sea of Tranquility. And we should be seeing the craters Gilbert and Kastner shortly to the south of their flight path.
Roger 11, we're watching the Disky now, and still coming in beautifully on the TV.
The spacecraft faced around backwards, looking back.
Right side of the screen at the present time, there's a triple crater with a small crater between the first and second, and the one at the bottom of the screen is Schubert Y. Zoom in, it does have a central peak in Schubert Y. Actually several of them, and you can observe those. But the rim craters at the bottom of your screen. Roger, we're seeing the central peak quite clearly now.
Our view of this tomorrow will be much closer, of course, and be down a good deal closer to the lunar surface.
We're zooming in now on a crater called Schubert N. Schubert N, very conical inside walls, and the bottom appears to be nearly flat. Look at theta on the Disky. It's stabilized and is holding steady now. Roger. Looking out the window, I can see a number of small craters on the bottom of Schubert N. We're coming up on the foaming sea, where I'll be doing some P-22 marking on a crater of my choice, named Crater Camp. Okay, we'll be watching for Camp. And notice register 3 has reversed itself and is heading back the other way now without any pitch thruster firing. Roger, Mike. We confirm that you've changed the direction of your pitch rate.
Looking directly down on the moon from 100 miles over it as they move out of Smythe Sea into the foaming sea on their way toward the Sea of Tranquility.
Generally speaking, the crater's tendency seems to be to pull the LEM down toward the center of the moon as in a gravity gradient experiment. Roger 11, we copy. It may have something to do with mass times, or it may... Roger, we've got... it may have something to do with mass times, or it may just be the peculiarity of the Disky display. Okay, we've observed the behavior of your Disky. I think we've got the data here to work on it. Let us grind around a little while on it, and we'll report back to you probably in a rev or two. Okay, well, in the meantime, I'm going to pitch down toward 315. Roger.
That's Mike Collins, who's flying in the left-hand seat, Spacecraft Commander Neil Armstrong's ordinary seat.
Three horizontal craters that you now have in the field of view are immediately underneath the ground track. The right hand and the largest crater that you see is Cubiago P.
It's Armstrong talking.
Roger, we concur on the identification of that crater.
Arago B. the crater Neil Armstrong has identified. A small crater, as lunar craters go, one about 4 miles.
We saw you coming up on landmark Alpha 1 here shortly. Roger, Mike 7, his first look at Alpha 1 at the present time.
These landmarks, like Alpha 1.
Yeah, it's a great, bright crater. It's not a large one, but an extremely bright one. It looks like a very recent, and I would guess, impact crater with rays streaming out in all directions, which should make space, or the correction of foaming sea, easy to see coming up on it. Now, Crater Camp is one of the smaller ones out on the floor of the foaming sea.
We've been some 17 minutes now into this television pass, standing by, continuing to monitor.
They're now about 80 miles east of landing site 2 in the Sea of Tranquility, moving past the crater Kant, which you saw a moment ago.
This view is from about 110 miles up, too.
Right, they've reached their low point, or parasynthion around the moon, and are heading up toward the high point. And are picking...
the television camera. Look at that.
Okay, we show you
clarity
over the Sea of Fertility now, and ought to have Langrenus down south of Trek a few degrees, about 9 degrees south of Trek.
Yeah, the crater that's in the center of the screen now is Webb. We'd be looking straight down on it at about 6 minutes before power descent. It has a relatively flat bottom to the crater, and you can see maybe 2 or 3 craters that are in the bottom of it. On the western wall, the wall that's now nearest to the camera, near the bottom of the screen, we can see a dimpled crater just on the outside. And then coming back toward the bottom of the screen and to the left, you can see a series of depressions. It's the type of connected craters that give us most interest to discover why they're in the particular patterns that they're in. I'll zoom the camera in and try and give you a little closer look at this.
Roger, we're observing the dimpled crater now. The central peak that we can see on the orbiter photos doesn't seem to stand out very well here.
Well, they're not central peaks, they're depressions in the center.
Roger.
And you'll notice on the pitch thruster activity, I put in a dozen minimum impulses and pitch down, and I'm still far from correcting back to 315. We're moving the camera over to the right window now to give you Langrenus. It's several central peaks, and
Roger, we got Langrenus in our screen now.
And Langrenus is an enormous crater about 160 miles south of their flight path, a crater about 85 miles in diameter. And that's Collins and Armstrong zooming in the camera for a close-up view of it.
Okay, 11, this is Houston. We're getting a beautiful picture of Langrenus now with this rather conspicuous central peak.
Moving along into the Sea of Fertility.
Doesn't look very fertile to me. I don't know who named it. Well, it may have been named by a gentleman whom this crater was named after, Langrenus. Langrenus was a reasonably accurate maps of the moon.
Roger, that's very interesting.
Now, that sounds better for our purposes than the Sea of Crises.
Amen to that. Okay, it looks like you're coming inside now on the camera.
Well, I can't get behind the steel monitor. I'll bring the focus in, but we're going to be looking down past one of the LEM quads.
and one of the antennas almost straight down at the ground track that we'll be seeing coming in. Now, I guess this is maybe 2 or 3 minutes before power descent.
That's Lunar Module Pilot Buzz Aldrin telling what we'll be seeing outside the window here of some of the LEM's thruster quads, or little reaction control system engines.
That should put the LEM structure about in focus. I'm going to move it out to infinity and then expand the field of view.
That's Buzz Aldrin, and we're looking at one of the LEM reaction control system quads. He's now zooming past it.
Crater Secchi is out my window now, window number 2.
Apollo 11, this is Houston. We show you coming up on the Terminator at 78:53, about 7 minutes from now. And we've also got the LOI-2 and TEI-5 pads ready for you after the TV, whenever you want to terminate over.
Roger.
And we're getting a good view of the track leading into the landing site now.
Apollo 11 sweeping along at about 3,700 miles an hour over the moon.
How far are they from the landing site now?
Okay, it looks like we had Secchi K go by about 10 seconds ago, coming up on Apollo Ridge.
And they're now about 300 miles.
And in the right-hand portion of our screen right now, we can see Messier, Alpha, and Bravo with the light-colored rays streaming off in one direction.
Capcom Bruce McCandless saying what Apollo Control sees from the same TV picture we're all looking at.
I don't know if you can make out, but in the Sea of Fertility, there are a number of craters that are just barely discernible, old craters whose outlines are just barely able to be seen.
Roger, I think we can make them out. The color really enhances our ability to discern features and craters over what we see in real time on our black and white monitor.
Right. At these low sun angles, there's no trace of brown. It's now returned to a very gray appearance, and like the aqueous says, it has a look of plaster of Paris to it at this sun angle, which is completely lacking at higher sun angles.
Roger.
We're now some 25 minutes into our television pass.
And shortly, just along here.
This is very close to ignition point for power descent. Just passing Mount Maryland. That's a triangular-shaped mountain that you'll see in the center of the screen at the present time, with the crater Secchi Theta on top of the far northern edge of the mountain. I think we're getting a good view of Mount Maryland and of Secchi Theta.
That was Neil Armstrong. They're about 260 miles east of the landing site, just about the point, as Armstrong was saying, where they'll ignite the LEM's descent engine tomorrow to begin their landing.
What we call Boot Hill occurs 20 seconds into the descent.
And it's easy to see what's on Armstrong's mind.
Sure.
Watching this pass with a great deal of interest in Mission Control Center is Pete Conrad, the commander for the Apollo 12 mission.
Right edge of the screen, Censorinus T. Now passing the 1 minute point in power descent.
Roger, and for your information, your current altitude is 148 nautical miles above the surface.
The clustered Censorinus craters.
I'm unable to determine altitude at all looking out the window. I couldn't tell whether we're down at 60 or up at 170. I bet you could tell if you were down at 50,000 feet. I wouldn't be surprised.
The clustered Censorinus craters will be hearing more of tomorrow right along their flight path as they do the power descent burn.
Some steep ridges here, the edges of old craters that were photographed by Apollo 10, and the crew of Apollo 10 was very impressed with the steepness of these ridges when they came over them at about 50,000 feet.
Roger, we can observe they're also steep even from this altitude. You've got quite a shadow being cast by the sun at these low angles.
The entire surface is getting considerably darker than the surface that we looked at previously when the sun was quite high above us. The crater in the right crater in the center of the screen, the smaller one, is Censorinus.
Roger, and we show you a little over 1 minute from the terminator at the present time.
Censorinus, a crater about 18 miles in diameter, and what Armstrong is doing is flying right down the glide slope.
The picture you're receiving, I think we ought to open up the f-stop some as we approach the terminator.
Yeah, the brightness is still doing quite well. You can go ahead and open it up a stop or two. The automatic light level compensation seems to be working beautifully.
It's going to get dark at about the same time they pass over landing site 2 as they hit the terminator.
That's a good picture of Boot Hill.
One of the landmarks into the
3 minutes and 15 seconds into the descent.
Roger, we're seeing Boot Hill now.
And the next crater coming into the bottom, that's Duke Island right there, and to the left, the crater, the largest of the crater near the center of the picture right now is Maskell and W. This is a position check during descent at about 3 minutes and 39 seconds, and it's our downrange position check and cross-range position check prior to yawing over face up to acquire the landing radar. Past this point, we would be unable to see the surface below us until getting very near the landing area.
And what Neil Armstrong is saying is at this point...
I imagine you get a real good look at that tomorrow afternoon.
We won't see it this way tomorrow afternoon, of course, because the little TV camera inside the command module won't be with them.
Continuous reel is the one that was referred to in Apollo 10 as Sidewinder. Good name, too. Sidewinder, Diamondback. Looks like a couple of snakes down there in the lake bed.
They would now be at about 37,000 feet over the moon if they were in the landing procedure.
And we're approaching the terminator now. You can see the contrast increase, and only the sunlit side of the bridges remain illuminated, while the dark sides in the shadow will become completely black.
11, this is Houston. The picture is getting a little grainy now. You might go ahead and open up the f-stop. into darkness. That one crater is the upper part of which you see, lower part completely in darkness. A small, well-defined crater is bulky, which is about a beam of the landing site.
Roger, we can just see it looks like a little less than half of its rim right now.
And it would appear that the orbit of Apollo 11 is perfect.
Just barely some features on the surface, maybe from Earthshine.
The crater Moki there, about 30 miles south of their track.
Are you wide open on the f-stop at this time?
Where we are. Yeah, and it looks like we're just about to get the sun coming into the lens, so we'll have to move the camera away.
Roger.
We can't see any Earthshine or any surface features at all in Earthshine now due to the fact that the lamp is very bright and is causing our pupils to contract.
Neil Armstrong took us through a dress rehearsal, or a typical instrument landing glide slope procedure showing how he'll do the PDI, the Power Descent Initiate Burn, tomorrow to bring Eagle, their lunar module, down to the landing site, lunar landing site 2 there. And even more important was that he was right on the money, right on the right track, but not 4 or 5 miles south, as Apollo 10 had been over that same site. Apparently, the LOI burn, the trajectory and navigation guidance work, has been absolutely flawless. Armstrong appears to be all set up. Well, and as one of the men just said, looks like the LEM is ready to go down, wants to go down.
Well, it's in a way a million light years between the flight of the Wright brothers at Kitty Hawk, but it's not so very long at that when you stop to think of the actual calendar time. But of course, there have been tremendous strides. Nobody could have dreamed, no realist, I guess, could have dreamed at the time of the Wright brothers' flight that less than 70 years later, people would actually be on the surface of the moon. We have a film package for you. ABC's Don North has put it together to just trace the history of flight. Here's Don North.
Incredible as it may seem, there is only 66 years between this, the first successful aircraft to fly, and the flight of the Apollo 11 spacecraft. 66 years between the flight of Wilbur Wright and Neil Armstrong. It was in this aircraft, a frail combination of wire, wood, and cloth, on December 17th, 1903, that Wilbur Wright launched on the sands at Kitty Hawk, North Carolina, and flew for 12 seconds. He covered a distance of 120 feet. A modest beginning, with few Americans realizing the significance of this achievement. The Wright brothers alone seemed to realize the significance of what they had done. Later, Orville Wright said that it was the first time in the history of the world in which a machine carrying man had raised itself by its own power, raised itself into free flight, and sailed forward on a level course without reduction of speed, and finally landed without being wrecked. A single still photographer was there to record the event. He made this photo. There were no newsmen present. Later, only one newspaper, the Norfolk, Virginia Pilot, printed the story, but they got most of the facts wrong. This film shows an early glider flight about 1902. It was through their experiments with kites and gliders that the Wright brothers developed their successful aircraft. Seen directing operations here, Wilbur Wright on the left. After 1903, the Wright brothers flew their planes in Europe for the governments of France, Germany, and Italy, and achieved worldwide attention. This is the younger Orville Wright. In 1909, they demonstrated this aircraft for the U.S. Army at Fort Myer, Virginia. With Lieutenant Frank Lahm as the passenger, Orville Wright, shown here, satisfied the Army's requirements, and Secretary of War Howard Taft awarded them a prize of $30,000. It was in Italy, before King Emmanuel, that some of the finest film of the Wright brothers' early flights was made. The European powers were very interested in developing the airplane for military purposes, and later Orville Wright was to regret the use of the aircraft he developed in war. He said, "I feel about it as much as I do about fire. I regret its danger, but I'm glad the human race discovered it." This is a catapult launch similar to the idea of a launch from a modern aircraft carrier. There was a brave cameraman here. Notice they never flew very high, about 30 to 50 feet in those days. They weren't too sure of themselves. It was during this demonstration that the first film was made in the air. An intrepid cameraman climbed aboard beside Orville Wright, and they took off down the launch pad to take the first film shot from an airplane.
All right, they've just received the go signal from Mission Control to undock. That will take place around on the far side of the moon. So, Jules, Eagle and Columbia will now come into their own, won't they, on their own?
They're on their own, and they are pretty well committed at this point, and no one's particularly concerned about it. Eagle has checked out amazingly well, far better than it, or most lunar modules and most command modules have done on the ground, and certainly better than any of the astronauts have been able to do in the simulators. It seems to be the story which Stafford and Frank Borman and many other astronaut space commanders have told us, that when you get up there in the real vehicle, it's much easier than in all the practice sessions. It's much easier than in the hundreds of hours in altitude chambers and in test rigs on the ground. The real thing is always easier to fly. And this is the way it will be. This is the way it is now, we should say, just before undocking, which takes place on the far side of the moon, with the command module, Columbia, on the left-hand side of our frame, of course, docked to Eagle, the lunar module, both of them passing in an orbit some 60 miles over the moon. Actually, the orbit varies between 55.9 and 63 nautical miles over the moon's surface. Mike Collins alone now in the command module. Let's go to Houston for a little air to ground in these final moments before loss of signal. We just heard Collins talking to Capcom Charlie Duke. Let's see if we can pick them up again. There's the scene in Apollo Control in Houston. Some tenseness at the consoles, a quiet scene, a busy scene, as they watch and wait, as Flight Director Gene Kranz, an expert at this kind of thing, the flight director in charge of the descent maneuver and the lunar touchdown, has his team drilled.
Here we go. Go ahead, Columbia, over. Roger, there'll be no television in the undocking. I have all available windows either full of heads or cameras, and I'm busy with other things. We concur, over. Eagle, Houston, we'd like you to select aft Omni now. It'll be good for both LOS and AOS, over. Roger, going to aft Omni.
And that was Mike Collins confirming that the live television he'd hoped to do of the undocking now cannot be done. They're switching antenna positions, which is why the signal has suddenly gotten scratchy there. As Eagle and Columbia go over the hill, as the astronauts call it, around the western side of the moon.
Apollo 11 is on the far side of the moon, and we are about 25 minutes away now from the point at which they will undock, actually separate the two spacecraft, Eagle and Columbia. And Jules Bergman is down in our mock-up of Eagle with Dick Sprague. Jules?
Frank, we're in our own Eagle, if you will, our lunar module mock-up here at ABC Space Headquarters with Grumman consulting pilot Dick Sprague, who's right now in what everybody's going to hear is the CDR station, the Spacecraft Commander Station, where Neil Armstrong will be flying Eagle down to the landing. Uptight, if you will, to that triangular window, Dick. Is that right?
Right. This will be Neil's position as he's approaching the surface.
Right. Now, what, Dick, these landing scribes or the LPD, the landing point designator, looks like an old-fashioned reticle, a crosshair, and a telescopic sight on the rifle. What does Neil do with that?
Well, when he stands in the correct position, or the design eye position, aligns these scribes on the inner and outer glasses, he is then looking out at a point on the lunar surface when the computer tells him to.
Right.
And it tells him how many degrees down on that scribe line to look. He will then be looking at the point that the computer has decided to land him at.
For example, if it says 33 degrees, as it nominally does in the flight plan at low gate, that's where 500 feet above the moon's surface. That's where Neil wants it to be, and Buzz, I'm standing in Buzz Aldrin's position here, Buzz wants it to be, for the actual lunar touchdown. We're going to take you through that touchdown now via animated film, picking up with the undocking that's due to take place about 25 minutes from now on the 13th revolution of Eagle and Columbia, their command module, as they pass behind the moon, the far side of the moon. As the animation shows, the two vehicles undock and pull away from one another, and Neil and Buzz are there in Eagle, their command module, getting ready to start down. There they are, tight at the windows, as Dick Sprague showed us. The descent engine fires, that 10,500-pound DIPS engine, as you'll hear it called, in the DOI, or Descent Orbit Insertion Maneuver, which will lower their altitude from 60 miles around the moon, which is what is it now, down to the 50,000 feet where Tom Stafford and Gene Cernan in Snoopy, their lunar module on Apollo 10, got to. Then after successfully getting down to 50,000 feet, and what really is a continuous maneuver, they do the PDI, or Power Descent Initiate burn, which takes them from 50,000 feet down to the moon's surface. PDI begins 260 miles west of the landing site in the Sea of Tranquility, slowing them down all the way until they finally do the final descent vertically like a helicopter, coming down very, very slowly to what should be a smooth landing. The actual landing area, a 3.2 by 1.6 mile ellipse in the Sea of Tranquility, about 1.5 miles by about 4 miles in size. All the maps so far indicate that ellipse is smooth, that Armstrong and Aldrin should have no trouble. That's the way it'll look as they touch down on the moon's surface.
Not long ago, I talked with Neil Armstrong about, well, basically the dream that will climax with Apollo 11. You're supposed to be, and you are, a pilot, not a philosopher, but you are going to be the first man to land on the moon. You must have thought well beyond the technical, purely scientific aspects of this mission. So I want to ask you really kind of an impossible question, but you're the man to give the answers. What do you think this mission will tell us about man?
If we are successfully able to execute a touchdown and return, it's going to give us an unmeasurable amount of confidence. I think that's probably the greatest result of the flight. It's going to assure those people who have been spending long hours late at night for many years in the computer labs across the street and in the simulations over in the other building and the program offices that the almost staggering technical job that they tackled is in fact possible for man to conquer. And given that confidence, we will then be in a much better position to accurately judge what we should tackle in the future. It won't be marred by a lack of understanding of what can and can't be done. It can be judged on its values.
Do you think it might help us to maybe solve some of our less exotic problems here at home, on Earth?
Well, I certainly hope that that we would take the more successful approaches that have been used in this kind of a program and find ways to apply those approaches to other problems. I don't necessarily agree that just because these people have in this approach have been successful that we should take their resources away from them and give them to some other people who have been less successful in their endeavors.
I get the impression you think we might be able to do both.
Well, I certainly think we can. We're a great country. We have a lot of abilities, and when we direct our efforts toward an understood goal, we usually solve the problems.
You know, I think I was wrong in putting that question to him in the way I phrased it. He is a philosopher, too, as well as a pilot. He's a young man who means what he says and says what he means. We're back in mission control now to see if we can't get some more communication.
Houston, Columbia, my disk is reading 4.9, and X, 5.0 make it, and EMS 105.4, over.
Roger, copy, Columbia, looks good, over.
Okay.
We should have confirmation of the separation burn momentarily. Collins said a few seconds ago to Armstrong and Aldrin, you've got a fine-looking flying machine there, meaning he'd given them his go.
Houston, we'd like you to terminate average G, over. Roger, info.
B, he said.
Just confirming and see. Is that commercial B? B.
We're waiting now to get confirmation of this separation burn.
Right, Frank. A quiet time there. The burn should just have happened.
They'll still be in visual sight of one another, though, won't they?
Right. They'll stay in visual sight for quite some time as they slowly drift apart. Collins does a small reaction control system thruster burn with Columbia's thrusters. Slowly pulls away and watches Eagle. Indeed, he can see Eagle all the way down, almost to landing. You'll see it certainly.
This is Apollo Control. That separation maneuver was performed as scheduled, giving the command module a delta V of about 2.5 feet per second, which should give a separation to the two vehicles of about 1,100 feet at the beginning of the descent orbit insertion maneuver.
This is Frank Reynolds with Jules Bergman at ABC Space Headquarters in New York. We should tell you what Armstrong radioed to Mike Collins as he moved away in Columbia after the separation burn. He said, "You're going right down US 1, Mike." Collins moved away, and now they are flying in tandem, so to speak, until the time comes for the DOI, or the descent orbit initiation, when they will start down in Eagle toward the surface of the moon, and Mike Collins in Columbia continues, of course, to orbit around as sort of a watchful mother hen to watch every move they make. In the event they encounter any difficulty on the way down, he does have the capability to go to a certain point, and try to rescue them. And, of course, he'll be very happy to see them come back when they crawl through that tunnel again late tomorrow afternoon.
He can get pretty low, Frank.
Well, how far down can he go? He said the other day about 10 miles, didn't he?
It varies a little bit, but Collins has apparently rehearsed the fine art of rescue in abort modes to the point where he can actually get the Columbia command module down to 20 or 25,000 feet above the moon's surface if he has to. In the unlikely event that all the lunar module's engines failed and Armstrong and Aldrin couldn't abort by themselves to get back up to the Columbia. So Collins can get down within 5 miles of the moon's surface.
Within 5 miles.
That's pretty low.
It sure is. He's at about 69 or 70 now.
Remember, I think you were there when I talked to Mike that day, and Mike's principal concern was no one is sure how high some of those craters, how low some of the craters are, and how high many of the mountains are on the moon's surface, and you're coming along, it's like avoiding television towers and buildings in an airplane coming in a rainstorm. You've got to be darn sure what's going on. So that's one big thing he's worried about.
Yes. You're like trying to land at, say, one of New York's airports without knowing very much about how the buildings were around New York. Well, we thought we'd have some heavy thinkers here now for a change and take a small break while Jules and I get a moment of rest. And we're going to have some thoughts by three very important people about why we should be going to the moon. Here's Bill Moyers, the editor of Newsday, Marshall McLuhan, the philosopher of communications technology, and Ian McCard, a regional planner, amateur ecologist, author of Design with Nature. ABC's Howard K. Smith asked Mr. McCard about the motives that send Earthmen to the moon.
I would give all honor to the astronauts and NASA for this, phenomenal adventure, but it seems to me there are two motives here, one of which is good and the other, I think, quite bad. One, the good motive is the increase in man's knowledge. The bad motive, I think, is the motivation of conquest, and I think our attitude to nature has been throughout the whole Western tradition one of conquest. We talk about conquering Mount Everest and conquering the moon and conquering space. And we have, you know, traditionally this whole culture, thick, low-browed, dull-witted,
territorial,
laying bludgeoning strokes across, you know, the world-life body, destroying and singing paeans of self-praise as we go. And I think there is an aspect of this, you see, in the conquest of space, that it is really based, it's the same witless...
It's metaphoric, so when you
man.
say the conquest of space, you mean it's a metaphor?
Oh, I think it's not a metaphor. I really believe the Western tradition does believe that man has a moral duty to conquer nature. I mean, he is exclusively divine, or so the Genesis tells him, given dominion over life and non-life, and joined to subdue the earth. And by God, the whole Western tradition, Judaic and Christian, has tried to give the best evidence of this dominion and subjugation that it possibly can. And the conquest of space is just one of the spin-offs of this arrogant, anthropocentric, witless, clottish man who insists in subjugating the earth and all creatures.
I don't look at it that way.
I was going to ask you.
I think man is essentially an explorer. He's always reached out into the unknown, and Mr. McLuhan said earlier that if something can be done, it will be done, and man is going to determine that he can do this. I think it is not a greedy, avaricious reach for something that he would like to control as much as it is for something about which he would like to know more. And I think as long as there is something unknown, man will be trying to reach for it. What I've learned from all of this is that man also, as a political animal, has the capacity to organize himself and his peers in such a way to attain a goal that a decade ago seemed to be impossible and seemed to be forbidding. And what I hope that we can do from this is to see the difference that exists between what we've done in space and what we yet have to do on Earth, and organize ourselves to achieve the goals which will affect the lives of billions of people on the Earth, as well as the lives that will be affected of the few men who will make it into space.
Bill, you were in a high place in government at a time when this program was launched. Do you think that it's been a wasted effort, that the money, it has been a perversion of resources and skills?
No, I don't, for this reason. We were not doing very much in the social and domestic field in the late 1950s when we were not searching for the moon or reaching into space. We have done more on Earth since we have been doing more in space than we ever did in the decade before. That's a syllogism, perhaps, which proves nothing except the fact that this nation is so wealthy and so rich that it really has the capacity to do what it will organize itself to do and what it establishes as its priorities.
But, Mr. Moyer, have you considered that the Russians, who have never had a 19th century, who have many less resources than we, have also accomplished more or less the same goals in space?
But at a greater price. You see, their GNP is such that they could not carry on a consumer revolution at the same time we have been doing that.
All right.
And so they had to give up something. I don't think we have to give up something. I think we do, because it is so much easier to reach a goal that has few political obstacles in front of it than it is to try to do something about some of these problems which have political
It's just a kind of luxury for us to play with these things, whereas it's life and death for the Russians.
No, it's not life and death with them. They made it a matter of life and death.
On the other hand,
the allocation of their very meager resources.
On the other hand, with Sputnik, they created a very witty pun, which was carried out visually. Little fellow traveler. They put this little fellow traveler as an environment around the planet, a planet that was terrified of fellow travelers, and they put a little one out there to reassure us that it was friendly.
They didn't create the pun, Mr. McLuhan, you did.
Well, the word Sputnik means little fellow traveler in Russian. And it was done at the time when fellow travelers were rather a menace in our world.
But they did it for a very esoteric group of men of whom you are the paramount chief.
No, I'm very flattered, but I heard that from a great many other people. I didn't probe into the etymologies of the word. But it is, I think it's worth considering, since they do have a sense of humor, what the Russians had in mind in the complementarity of this current effort.
Oh, yeah. I think at least in the beginning, Mr. Smith, they had a military purpose behind their space effort. And I think this is one of the reasons that our leaders at that particular time, particularly in 1960 and 61, were motivated out of a sense of reaction, even to some extent fear, which has been translated into the prestigious reach for to be first in space. But I think they really had serious military motives behind their
are there, when you say serious military motives, I shouldn't think military motives half as serious as many others, including educational. But when you attach the word serious to military, I don't.
It can be attached to almost any word.
Well, there are many military efforts that we're making that are not serious in the sense of their relevance.
You don't think of
in the sense of
you
the
don't
relevance.
think of Apollo 11 as having any relation to our own military interests?
By all means, the present head of the Apollo program, who is a general, indicated today that he will be leaving the Apollo program a few days after the flight in order to go back to the Pentagon to apply the techniques he's learned in the Apollo program to our defense effort. So I think, to go back to one of your first questions for 1 second, you said, what is the value of this? Well, there are many esoteric values that are still to be realized. There are many long-range projected values that the millennia will realize, but the immediate value is military. Let's face that. The practical, significant application of our space effort, if it has any pragmatic value whatsoever, is basically military.
Let's ask ourselves in long-term projects about the meteorological possibilities of the conquest of moon space.
You better ask him.
Can we consider the possibility of space platforms that might serve the control of climatic conditions eventually on Earth?
I haven't a finished idea. I'm the wrong man to ask about this. I do know that satellites orbiting the Earth, of course, can have an enormous utility. They now have elaborate sensors. The Interior Department is going to send up another satellite. Is it not Eris? And this beautiful creature will be able to monitor the Earth continuously, and we'll be able to observe things as delicate as the amount of carbon dioxide or the productive fertility or health of crops, sedimentation in rivers and so on. The whole dynamism of natural processes may be continuously monitored. This material could be digitized into computers immediately, and that material can be used by people like me to make regional planning decisions, and this is enormous social utility.
A historical moment, a historical point here. Back in the early days of the space effort, and even into the acceleration of the Apollo program in the early days of 64 and 65, the men who brought to the president, to the White House, the projections, the facts, the research, the figures, were very realistic about the immediate practical effects of this whole program. As far as interplanetary travel is concerned, it will remain for generations to come a very esoteric feasibility, for the very simple reason that it'll be a long time and take many billions of dollars before we can develop the kinds of programs that will make interplanetary travel, vehicles that will make interplanetary travel available to more than 3 or 4 men at a time. To go to the Mars, for example, is a 2.5-year round trip.
Mr. Moyers, you are working on the assumption that the present forms of fuel and hardware